For some reasons, my computer is just slow. Okay, great. Now, the last time we were looking at the continuous system, and we came to a point of the dilution, critical dilution rate. For those, for those that were unable to attend the last lecture, we said if you increase first, this is how a setup of continuous system may look like, which you have two peristaltic pump 2 and pump 4. Pump 2 takes from the feeding tank into your reactor, and pump 4 takes out the used medium from the feeding tank to the storage tank. And we said, based on the previous equation, that we showed that your dilution rate can actually be used to control the specific growth rate, right? For those that miss it, that your dilution rate can be used to control the specific growth rate. We agree that you can increase the growth rate in this system. Yeah, we can increase the growth rate, your specific growth rate in this system by playing around with the dilution rate. But there is a point at which it would not be longer possible for you to continue increasing the growth rate of the cells by playing around with the dilution rate. For example, we said when cells are multiplying within these reactors, and at the same time, the overflow device is taking out portion of cells, if you increase the dilution rate, there will reach a scenario in which the growth of the cell can no longer match the dilution rate, and cells begin to be washed out of the system. Whenever your dilution rate exceeds that point, which actually corresponds to the maximum specific growth rate, as your friend, your classmate said last time, when you reach the point, you have actually passed the critical dilution rate, the dilution rate at which the growth rate can no longer support, the growth rate can no longer match that dilution rate. That's your critical dilution rate. And something interesting is that at the critical dilution rate, if you have a reactor, like I said, one of the exam questions, if you have a reactor, a continuous system that operates over a long period of time above the critical dilution rate, obviously cells within the reactor will be washed out. You end up with X equals 0 because cells are no longer in the reactor, okay? And the substrate concentration in the reactor, since we don't have cells to consume the substrate, that implies that substrate begins to accumulate in this reactor. And please, can you switch off your microphone unless you want to ask a question, please? If you want to ask a question, just unmute yourself and ask. Great. Now, if you react to a typical question which can be given to you is this: you have a reactor operating above the critical dilution rate over a long period of time. Find out what becomes of the cell concentration within the reactor. Obviously, cells will be washed out to end up with those cells. Another aspect that I think we cover, should come briefly on it, was on the idea of process contamination. Okay, again, I use this diagram to explain to you what happened when there's a contamination in your reactor, because that's the key challenge in using continuous system. Let's assume that you have X1 cells in this reactor, and X1 has its own maximum growth rate. And subsequently, there's a contaminant, let's call it X2, that finds its way into this reactor. And X2 can grow faster than X1. Obviously, X2 will grow, and the growth of X1 will be dictated by the leftover nutrient in this reactor. Consequently, since you have pump 2 and pump 4 that operate at the same flow rate, if you revert back to what we said, that if the growth rate of the cell is not matching the dilution rate, such cells will be washed out of the reactor. Now, you started with X1, which was your genetically modified cell to produce, let's say, insulin. And after 24 hours, there's a contamination, that is X2, find its way into your continuous system. And the X2 can grow faster than X1, okay? If X2 multiply faster than X1, that implies that the growth of X2 will match the dilution rate operating in this reactor. Consequently, the substrate left over, or better still, X2 will dictate how much nutrients will be left in this reactor for X1 to consume and grow. And since the growth rate of X1 is no longer matching the dilution rate, X1 will be washed out of the reactor because X1 is multiplying at a lower rate compared to the operating dilution rate. Now, at long run, X1 will be washed out of the reactor. X1, which was your initial strain producing your insulin, will be washed out of the reactor. You'll be left with a population of X2. X2 produced nothing. In other words, the contaminant has taken over the continuous system. Another aspect which I explained to you was, which I asked you to think about last time, was a scenario in which, in this system, you have taken all the necessary aseptic conditions to prevent contamination from outside. And you have, for example, your X1 strain mutating within the reactor and producing X1 prime. X1 prime is a mutant could be a mutant from your initial strain, and the X1 prime grows faster than X1, but produces nothing. That is, doesn't carry the gene required to produce your desired product. That's another case of contamination, but we refer to it as a contamination from within, right? Or strain degeneration. And the question given to you last time was, how can you prevent such kind of contamination from within the continuous fermentation system? And I asked you to reflect on that, right? You reflect, tell me what you think, how can that be controlled? Of course, you know for sure that if you're dealing with contamination from external contamination, if you observed all the aseptic techniques, sampling, and so on, you can to some extent reduce the risk of contamination. But in the case in which you have contamination from inside, you have strain degeneration, is it preventable? Because if you look at the setup of this system, by implication, the slower growing strain will be washed out of the reactor. You'll end up with a monoculture of the fast growing strain, okay? You're gonna end up with a monoculture of the fast growing strain. And the strain that's growing very slowly will be washed out of the system. Unfortunately, in that case, what is being washed out is actually your target organism, the one that initially was meant to produce your desired product. Okay, reflect on it. Tell me if you have an idea how the industry can operate and arrive at controlling the contamination from within, right? Then I ask you to take this problem and reflect on it. If you haven't taken it, you could grab it. You can grab it and spend a couple of time reflecting how you solve it. It covers aspect of continuous system with little calculation. Okay. Get it, reflect on it. The teaching assistant will definitely take you on the tutorial to provide the answer to the question. Okay. Then last week we started with the Fedbatch system, and with this diagram, it clearly illustrates that the Fedbatch system, you are feeding the reactor, but nothing goes out, right? And I said it was an hybrid system between the batch and the continuous system. That's the Fedbatch. If you go by the definition that we had on the batch system, in which nutrient goes into the reactor, you feed the reactors first. Sorry, the batch system, the reactor is sterilized. You do all the preparations and you run the system without interrupting it. Nothing goes in when the process has been initiated until the entire process is completed. Then you harvest it, you go to the downstream sequence of operations. Okay. The continuous system, we said something goes in, fresh nutrient goes in, the used nutrients, products are taken out. But here today, you have a new system that's in between the batch and continuous. This system, fresh nutrient goes into the reactor, but nothing is taken out until the process completed. Okay. Something also that we learned last time was that this was one of the most interesting or useful process mode in industry, because it helps in a number of things, which I'm going to repeat again to you in subsequent slides. We learned something in this system, which was, I'm sure a number of students did not agree with me, but after the explanations, the majority accepted my version of the fact. Sorry. At last class, we said the cell concentration in this system remain constant. Cells are growing, but the cell concentration remain constant, right? People are a little bit reluctant, but at long run, we all agree that cell concentration remain constant, simply because even though cells are multiplying within this reactor, there's additions of liquid, of nutrient into the reactor. In other words, cells are multiplying, but the concentration remains the same. However, the total number of cells within this reactor increases, right? The total number of cells increases, but the cell concentration remains constant. And that was termed as a pseudo-steady state or quasi-steady state in this Fedbatch system. And we say that the major difference between the steady state of a chemostat and the quasi-steady state of Fedbatch was that in the continuous system, I'm referring to the chemostat D, the dilution rate is constant. Whereas at the Fedbatch, D decreases with time. Okay, that's one of the things that we arrived at last time, that batch system, the continuous system has the steady state, whereas the Fedbatch system ultimately achieve what is called the false steady state, or the quasi-steady state, or the pseudo-steady state, okay? All these refer to the same phenomenon. Please, again, entire class, feel free, like I said previously, Nolu, Asanda, Teresa, feel free to interrupt if there's an aspect that you want me to elaborate on, okay? Feel free to interrupt if there's an aspect that you want us to elaborate on. Having said that, let's look at another aspect that I would like you to. Now, this slide is highlighted, is bold, is in red. The idea is that you read it many times, perhaps once in a week, right? If you can read it once in a week, that will help. Is Paula connected? Is class connected? I guess she's connected. Great. The idea here is that with the Fedbatch system, you're able to prevent the negative effects of the substrate concentrations inhibiting product formation. I put it that way. That is feedback inhibition, scenario in which product formation is inhibited by the presence of the substrate. I repeat, with this system, with Fedbatch system, it enables you to prevent the effect of substrate concentration on inhibition of product formation by feeding the reactor gradually in such a way that the concentration of the substrate will not reach a level that will impact on the product formation. That's the beauty behind it. And again, we learned in the previous class that Fedbatch system are extremely useful in the production of biopharmaceutical products, in the sense that many antibiotics are produced when cells are in the deceleration phase, and you want to feed the reactor at low rate You don't want to kill the cell, you don't want to starve the cell to death. In that way, you can use a Fedbatch system to gradually feed your reactor in order to achieve the mu value required to produce your desired product. And you have basically two ways of feeding the reactor, right? You can feed it constantly. You could have a constant feeding of a reactor, or you could have kind of exponential Fedbatch system. Now, if you look, let's look a little bit at the exponential feeding of the bioreactor. Cells, by definition, grow exponentially. That implies that you can actually, in order to maintain a constant D, a constant mu, your reactor needs to be fed exponentially. I repeat, by definition, we said at the pseudo-steady state, the dilution rate reduces, right? Dilution rate of Fedbatch system reduces. And in order to maintain a constant dilution rate, to maintain your mu or your D constant, you have to feed your reactor exponentially. And in the last class, I said, you can use a feeding system that's computer controlled to apply an exponential profile and maintain your mu or your D at the desired value. Can I proceed? By Vitra, can I proceed? Are we on the same page, Sianda? Are we on the same page? Should we proceed? Who's left behind? Okay. Okay, the last statement, the point was that cells grow exponentially, right? If you look at the multiplication of cells on a reactor, it goes exponentially. And you want to feed the reactor in order for the cells to grow, to have a constant mu, a constant specific growth rate, or to maintain D constant. It's ideal that the feeding pattern should be carried out in the exponential pattern as well. Let me take it with this analogy that may make it much more clearer to you. Think a little bit, let me give you an analogy if that will make sense a little bit. Let's assume that you have your little duck at home that you are feeding it, and you want it to grow, perhaps to add. It's a young duck. You want to feed it. You want to grow at a given rate. You want it maybe to add. You want the duck to add. I don't know. Well, you want it to grow at a fixed rate. Do you agree with me that if that duck is being fed, if you give it 1 gram of food from the day it was born, if you maintain 1 gram of food, you're going to reach a point whereby that growth rate, the rate of growth of the duck will decrease actually. If the dog was adding 1 kg every day and you feed it constantly, you agree with me that the demand in food, the demand in feed, nutrients will have to increase as time goes on. When you have a reactor, you have a population of cells that naturally grow at exponential, the rate of growth, they grow exponentially. You agree with me that if you decide, let's assume you decide to just put in 1 drop of feed, 1 drop of nutrients every hour without increasing it, the growth rate, the dilution rate will decrease in the Fedbatch system. Since D equals mu, the specific growth rate will go down as well. Why? Because D equals mu at the pseudo-steady state. Let me go back a couple of slides back to further illustrate what I mean. Going through this system, we said D equal F divided by, which is the flow rate, divided by the volume of the reactor. In a continuous system, the volume was constant, right? In the continuous system, the volume is constant. However, in the fed batch mode, you are feeding the reactor, but nothing is going out. By implication, the volume increases. If the denominator of this fraction goes up, increases over time, that implies that the dilution rate will go down. Okay? If you increase the volume, if you just increase the volume of the reactor, that will imply that the dilution will go down. You don't want the dilution to go down in your reactor, right? You want to have D equals mu. Just a minute. We said that you're going to reach a steady state where your D equal to mu as well, right? You also want to have D equals mu, but you want your fed batch system to grow at a constant mu. You don't want it to go down. The ideal scenario will be to feed the reactor in the exponential pattern. That is, you add more nutrient as time goes on. Then last time again, we look at different, how do you control the feeding in your reactor? We said you could have a dissolved oxygen diostat, where the feeding pumps or the feeding algorithm is connected to the dissolved oxygen concentration within the reactor. That is, based on the amount of dissolved oxygen in the reactor, the feeding pump will know how much nutrients should be fed in the reactor. You also have pH stat, in which, based on the change in the pH in the reactor, then your feeding pump will know when or how much nutrient to inject in the reactor. Again, you can feed it based on the carbon dioxide evolution rate. That will determine when and how much nutrient should be fed in the reactor as well. Okay, you can also feed it based on the cell concentration. That is, you are monitoring the cell concentration in the reactor, and based on the cell concentration, you determine how much nutrients should be fed in the reactor in order to maintain mu, the specific growth rate, at the desired value. Yeah, also look at a direct feeding mechanism in which you monitor the concentration of nutrients in the reactors. Perhaps you monitor the glucose concentration in the reactor and feed accordingly in order to maintain, in order to keep a stable nutrient concentration in the reactor as well. Now, these are the different patterns that enable you to feed your reactor in a fed batch mode to achieve the production of desired product. A typical exam question could be for you to describe the different feeding mechanism that can be applied in the fed batch mode reactor, to describe the different feeding mechanism that can be used. Okay, I would like you to read this mechanism, reflect on it, try to picture a little bit how can this really be applied. Before I proceed to another aspect that we have covered a little bit, trying to compare the continuous and the batch system, is there any question before I proceed? Any question? Any aspect you would like me to clarify before proceeding? Noluyolo, is there any aspect, Asanda? And the class rep, Paula, is there any aspect you want me to clarify before we proceed? Lile. Should I assume that you've understood everything?
Yes, we can proceed.
Thank you very much. Now let's look a little bit. Let's compare batch and continuous with respect to biomass productivity. Again, there's something very striking which I want the whole class to take into note of that. Class, I'm sure if in your exam you are given a questions to differentiate between yield and productivity, you will come out with the right answer. Class, I said when I was a student myself, it took me a substantial amount of time to understand that there was a difference between productivity and yield. Okay, and I want it to be clear to you that yield is different from productivity. If you refer back to our previous lectures in the batch system, which will find out how to calculate the yield coefficient. Again, in the continuous system also work at the yield coefficient. In other words, yield is different from productivity. Productivity has to do with time, okay? When you talk about the yield, you perhaps referring to the yield of biomass over the substrate consumed, right? You want to find out the yield of the biomass per unit of substrate. That's one thing. When you talk about productivity, you're looking at, if you talk about the biomass productivity, you refer to the biomass per unit of time, right? Always keep in mind, these are two different terms. Class, I repeat again to everyone, there is a difference between yield, process yield, and productivity in the bioprocess. Don't mix them up, okay? Don't make a mistake between the two. You should be able to work out productivity different from yield. Now, when we were comparing the productivity on batch system, we came out with a term which is called the unproductive time, right? If you look, sorry. You have what is called productive time. And in the batch system, your unproductive time is the batch time. This, if it is possible, just mute your microphone, but if you have a question, you can always unmute it, please. When you have a batch system, there's what we call the unproductive time, which is the time you use to sterilize your reactor, to emulate your medium. Whose microphone is making noise? Okay. Thank you for switching off your microphone. You have the times it takes to sterilize your reactor, sterilize the different accessories to be used in the production. You know, this actually refers to unproductive time because it's a little bit like a waste of time, okay? Because you are not producing any biomass under that condition. You are just preparing the batching time. That will have a negative contribution in calculating your productivity. By definitions, if you lower the time for preparing those accessories, I'm referring to TII and your TI as well. If you lower the time, if you succeed in lowering that time, your TI and TII, because of the time that cells are not really giving you a good biomass, you sterilized you spend it sterilizing the accessories, or perhaps waiting the cell to navigate through the lag phase and eventually enter the exponential phase and so on. These are regarded as unproductive time with respect to productivity. That implies that if you're able to narrow, to reduce that waste of time, if you can call it in quote a wasted time, you're going to boost up your productivity. Now, that's the case of the batch system. And again, take into account something, okay? Take into account something that the batch system needs to be reestablished over and over. That is, when you finish the first batch, you stop the process, you harvest your product, you proceed to the next batch in which you sterilize again the medium, sterilize again the reactors, go through the lag phase, which are both unproductive, and so on and so forth. That is, you're going to go batch by batch with so much of a wasted time. Now, if you take the case of continuous system, this is how its own productivity is computed. Again, it also has its own what could be called the waste time, which is referred as a TIII. It is a time whereby cells, it's a time prior to the establishment of the steady state, right? Now, the time for batching, or the time for preparing the system on the continuous mode, is only once. That is, you sterilize your reactor once, prepare your inoculums, cell will spend some time before entering the steady state. That is, the entire wasted time occur only once. And as soon as the system enters a steady state, it can run for a long period of time. In other words, you can minimize, or better still, in the continuous system, the wasted time, the unproductive time is minimized compared to the batch system. I repeat, we are comparing the batch and continuous for biomass productivity. Okay, this is where we are. We are comparing the batch and continuous for biomass productivity. And we said that the batch system has to repeat over and over. It has so much wasted time, so much unproductive time. Unlike the continuous system, it has reduced unproductive time. The TII is minimum compared to the time for batching the batch system. Now, based on those two definitions, the batch system is, the continuous system is more productive. I underline, the continuous system is more productive than the batch system, okay? Based on the fact that the unproductive time is reduced in the continuous system compared to the batch system. I repeat, the continuous system is more productive. You can write it down in your document, write it down in your note, that the continuous system is more productive than the batch system because the duration of unproductive time is significantly reduced in the continuous system. Because the duration of unproductive time is substantially reduced in the continuous system. Because the duration of unproductive time is substantially reduced in the continuous system. Okay, let's spend a couple of seconds on this slide. Class, when you have a batch system, look at microbial growth curve. At what point do you have the maximum biomass in the system? Class, Pomlile, you want to try? If you look at the batch system, I want you to picture a little bit the microbial growth curve, which you have the lag, acceleration, exponential, stationary, deceleration, stationary phase. At what point do you have more cells? At what point do you have the maximum biomass in the reactor? Do you have the maximum biomass at the beginning? Class, unmute yourself. I want to see you participating. Asanda, at what point do you have the maximum biomass in the reactor? Is it at the lag phase? Is it at the acceleration phase, exponential phase? At what point do you have more cells in the reactor? You can imagine the microbial growth curve. Can picture to guide you. Okay, you actually have the maximum cell concentration in the batch system when it's reaching the stationary phase. Cells are multiplying in your batch system, the population is increasing, and it is at the stationary phase where again as cells stop growing. In other words, the time at which you have more cells is just at the stationary phase. Okay? Now, take the case of the continuous system. Once the steady state is reached, whenever the system enters the steady state, cell multiplication is maximum and is being kept there for a longer period of time. But get me right, cells are not growing at mu max in the continuous system. The mu max, continuous system, write it down, please. Continuous system operate preferably below, or continuous system operate below mu max. Continuous systems operate below mu max. But you realize that you have the maximum cell concentration at that dilution rate that can be kept over a longer period of time. Whereas the batch system, it's only at the stationary phase that we have maximum cell concentration. In the continuous system, cell concentration can be kept high for a longer period of time. Know that what? That further emphasizes the fact that productivity in a continuous system is always greater than the batch system. Okay? That further substantiates the fact that productivity in this system is greater compared to the batch system. Class, can I proceed? Can we proceed? I want to assume that we're on the same track, right? Okay, I'll assume that we're on the same track, but however, if you have challenge, please thank you, Teresa, for approving that we should proceed. If you look at, sorry, we already mentioned this slide already, that productivity will always be high in a continuous system once you enter the steady state. Now, here's an additional advantage of a continuous system for industrial production. They said in a continuous system, once the steady state is reached, the cell concentration, the substrate concentration, the product concentration, and even the concentration of toxic substances remain constant. Okay, I would like you to underline this. Please, class, highlight this whole paragraph. That implies that you're going to read it, reflect on it whenever you are going through the lecture material. Once the steady state is achieved, of course, during the calculations, we all agree that at the steady state, ds over dt, the change in substrate concentration over time equals 0, right? That is, it remains constant, and that's what we are actually saying here again. Please reflect. You can take your memory a little bit back on the ds over dt, the calculation that we had previously. At the steady state, ds over dt equals 0. In bracket, substrate concentration remain constant. Now, we also mentioned previously that dx, the cell concentration over dt, remains 0. There's no change in cell concentration because new cells are taken out, right? Or better, sorry, the amount of cell taken out is equivalent to the new cell produced. I'm not saying new cells are taken out. Don't get me wrong, please. We're not saying that new cells are taken out, but the number of cells produced is equivalent to what's taken out. Therefore, dx over dt equals 0. Or in bracket, the change in cell concentration is 0. There's no change in cell concentration, or cell concentration remains constant. Now, something new I learned is that product concentration in such systems is also constant, right? And even the concentration of the waste material is also constant. And we said that that will help to reduce the control problems in such reactors. That helps in reduce the control problem because most parameters become constant once the steady state is achieved. If you look at the case of class, can I proceed? Zamo, is that information clear to you? That most, do you understand why we said cell concentration is constant? Why substrate concentration is constant and so on? Pumlile, is that clear to you? Do you clearly understand why we say those parameters are constant in the reactor? I want to believe that we are together and that you haven't put on your microphone, you haven't logged into Zoom, and the Zoom is, and you have left, you have left here, and you are somewhere doing some other activities. Paola, class rep, can I proceed? With the hope that you've understood why this parameter remain constant once the steady state is achieved. Paola? Do we proceed? Okay, I assume that we're on the same page.
Yes, we are.
Now, thank you. We said that in the batch system, the parameter changed, right? If you look at the case of the batch system, nothing is constant in the batch system. And we said that there's a change, the parameter change. For example, the culture can become too viscous, right? When you have perhaps a large production of metabolite or cells growth, it can become viscous. You got the pH that will be changing as well due to the metabolic activities and as well as the kind of the substrate being used. The temperature itself will change over time. In other words, you have the batch system is actually an unstable system. Okay, the batch system, you have everything that changes the system. What gives you have a false impression, class, we're together. You have a false impression that you have a stable system simply because during the exponential phase, cells have a constant mu at mu max, right? That's to give you the false impression that you are dealing with a stable system. But in reality, the batch system is an unstable system, which you have parameters that change with time. You have, for example, you have the substrate concentration that will not remain constant because it will cell will consume the substrate will reduce. The biomass concentration will not be constant because cells will be growing in the reactor. Nothing is being taken out. You have the pH that will change due to the metabolic activity of the cells. Cells are producing perhaps organic acid or producing other metabolites that will affect the pH. You have the temperature that will change due to the metabolic activity as well. And the only thing that gives you a false impression of having a stable system is the specific growth rate, which is mu at mu max during the exponential phase. Okay. Now, having narrated all those positive, good news or positive aspect of the continuous system, you will expect that continuous system will be how do I put it? The widely used preferred choice of the industry, but in real practice, there are some other problem challenge associated to continuous system, which is the one of contamination and equipment failure. Okay. Continuous system, we have seen that in terms of productivity, it comes quite largely beyond, it's quite superior to the batch system. And however, if you revert back to the contamination issues that we covered at the beginning of today's lecture, if you look at it like contamination issues, you realize that contamination in the continuous system is going to be a bigger problem than in the batch system. And if you refer back again to the advantage or those aspects where batch system were very useful, they said it is useful in those processes in which you don't want contamination. Whenever you have processes in which contamination is going to be a huge challenge, it's ideal to go through the batch system, which you could sterilize, carry out the batch, harvest your product, re-sterilize the reactor for the next batch. Okay, never forget, we have seen the positive aspect in terms of productivity with the continuous system. And again, unfortunately, we said such system could face tremendous challenge in case of contamination. We're still going to compare again, both for research and development, which I guess is the next slide. Okay, great. Class, just to refresh your memory, in the previous couple of slides, we're comparing batch and continuous for biomass productivity, all right? I repeat, in the previous couple of slides, we're comparing batch and continuous for biomass productivity. Now, let us compare batch and continuous for research purpose. Okay, let's look at which was more ideal if you really want to carry out some research in bioprocess development. Okay, let's have a look at this again. Now, the first point is the continuation of the previous one that says that batch cultures are characterized by continuous variations, the characteristics of the culture. Okay, let's look at it. That is, you have the biomass that will change over time. You have the product concentration that will change as well over time. It's not constant, it's not stable. And you have the substrate concentration that will not remain constant. We have already agreed on these characters. we also agree that it's only the mu max that gives you the idea of that gives the feeling of dealing with a stable system. Okay, it's simply because you have cells growing at mu, at the maximum specific growth rate, that you have a feeling that you are dealing with a stable system. In actual fact, biomass concentration is changing over time. The product is accumulating in the reactor, also changing, concentration change over time. And you have a number of parameters that are changing, that are not stable. Now, let's look at the case of continuous system. Keep in mind what you are trying to achieve. You want to compare batch and continuous for what purpose? For research and development purpose. Okay. We're comparing both systems for research and development purpose. We have already compared them in terms of biomass productivity. We're comparing again batch and continuous for research and development. Let me just quickly check. Yes, there's a question. There's a question that, so basically industry will still prefer batch system, even though there's high unproductive time. Yeah, you have many processes in industry that goes onto the batch and fed batch mode. Okay, the vast majorities of the processes will still be carried out on the batch mode or fed batch mode due to the challenges attached to the continuous system, even though it's highly productive. Now let's look at we're still comparing batch and continuous for research and development purpose. And the previous slide has just emphasized again that batch systems are unstable because you have the change in parameters over time. Now, if you look at the batch system, and I would like you to highlight this slide, please, the entire class. If you have a marker with you, if you have downloaded the material, highlight it yellow, and you read it many times because it contains so many useful information again. Right? This slide contains many useful information, and in actual fact, and a whole exam questions can be framed on this slide. It says that during the deceleration phase of the batch culture system, the onset of nutrient limitation caused the growth rate to decline from maximum value to 0 within a short time. And it's not possible to study the effect of nutrient limitations on the physiology of the microorganism. Now, let's look at it. I would love to go back to microbial growth curve for us to look at the deceleration phase. Please, if you can open your material on the deceleration phase or the microbial growth curve, look at deceleration phase. It's relatively short. You go from exponential, I'm referring to microbial growth curve, exponential, you pass through a very sharp, you pass through a deceleration phase that doesn't last for a longer period of time. Then you enter the stationary phase. And we say that during that phase, the cell will go from, let's say, mu max at the exponential phase down to 0 at the stationary phase. In other words, since that phase is very short, you cannot really assess the impact or the effect of nutrient on the cell physiology because that time is very short actually. In other words, in the batch system, if you were to study if too much or too little nutrient will affect the cell, it becomes difficult for you because of that transient, very short phase that will take place in the deceleration phase. Now, again, this is a very interesting slide as well, which I would like you to highlight again. They said is in a batch system, class, highlight this second slide as well, that the batch, if in actual fact, this slide has, this section of which I'm explaining today has been very, has been reoccurring in different assessment, okay? Now, I like giving you an idea where your assessment will come from, right? Especially for those that come for lecture. I like explain to you area that are likely to provide your exam questions. And that's the benefit of attending either Zoom or face-to-face lectures. Again, I said in the batch system, it is difficult to relate the causes and effects because physiological changes occurring in the system might have been initiated by change in the environment which took place some significant time earlier. I'm going to explain it to you. The batch culture system is not in equilibrium with its environment, okay? And I highlight that section as well. Now, when you said you want to have a system whereby if you modify parameters, you need to see a response in real time, right? Let me put it this way. If your neighbor sitting maybe with you in the classroom pinches you and you don't respond, you wait for 2 days and pinches him or her back, she may not know that you are responding to what he or she did to you 2 days earlier. Okay? Your neighbor may not know that this is exactly what's happening. If your friends slap you and you slap him back immediately, you would think that the slap, that's a real-time response. That's referred to real-time response. But if you don't reply at that time, you wait for 1 year and slap him, he may not actually know that slapping you was a bad thing. Now, let's bring it back to the reactor. If you make modifications with those external parameters affecting the process, in the batch system, you may not have the response immediately because the system is not in equilibrium with its environment. Okay? Whereas in a continuous system, you can actually play around with the dilution rate and look at the impact of dilution rate on the cell growth directly. Whereas the batch system is not possible because it's not in equilibrium. In a continuous system, you can play around with the dilution rate and see the effect of nutrient concentrations on the cell physiology. Okay? That's why you said here in the next slide that that the specific growth rate, well, is controlled by dilution rate, and using the dilution rate, you will actually play around with it and see how it's impacting the cell directly in the continuous system. Whereas in the batch system, since the system is not in equilibrium in its environment, changes what you observe, the behavior that the cells are displaying might have been initiated by some environmental changes that took place many hours earlier. Okay, you may not be able to really establish that what is referred to the cause and effect. You may not be easily establish a cause and effect because what the cell is responding to an environmental impact, so an environmental change that might have taken place substantial amount of time earlier on. That's why we say the batch system is not in equilibrium with its environment. And in the continuous system, you could actually play around with the dilution rate. You could and see the effect of nutrient concentration, for example, on the cell physiology. And it's also possible to have an idea of effect of other controlling parameters such as pH, temperatures on the cell growth, right? You can easily have an idea of such impact on the cell growth. Okay. I'm sure you are tired. I will stop here. We've virtually spent approximately an hour, and I will take a couple of questions if there are any questions. And yeah, if there's a couple of questions, I will take it. And that, just like I said, you have a new lecturer that will guide you in many other aspects of the module. If there are a couple of questions, is there any aspect on what we have covered on the batch, continuous, and Fedbatch that seem not to be clear to you and you want more clarification on that? Okay, I'm going to open for 1-2 minute questions if you have things you like us to, you think something wasn't clear. Hello, class. Is there any aspect, class rep, Asanda, Nolu, or else, Pumlile? Is there any aspect that is not clear to you? But notwithstanding, assume that maybe you haven't yet gone through the entire material. Go through it. If there is any aspect that is not clear, you could definitely let us know. We will make sure that things are properly explained. Okay, I will. I don't know, Dr. Malatu, I don't know if you are still connected.
Yes, Prof, I'm still connected. I'm with you.
Yeah, I think good page. You would like to speak to them, or you want Chinya to when it comes tomorrow with the.
I'll most probably be seeing the ones in Westville tomorrow. So now I think I can just introduce myself that I'll be taking over the bioprocessing section. And then tomorrow I'll also be running the revision on the microbial techniques, culturing techniques. Yes, and then the other information will be updated on the land. And then I believe Prof. Shina will be able to formally introduce me tomorrow before class.
All right. Thank you very much for joining us, and we appreciate your coming to assist us in this aspect. Thank you very much. Okay.
It's a great pleasure, Prof. Thank you very much.
Thank you. Thanks to the whole class, and have a beautiful day.